Welcome back, everyone. This is Professor Herring. In this video, we're going to do some extra practice problems from Chapter 14, Lesson 4, dealing with solubility. Let's begin. So, pause the video now, read over the question, and try and solve this on your own before I walk you through the process. Welcome back. So we want to know which of these is least soluble in water. When we talk about solubility, we're discussing the principle of like dissolves like. And we're looking for similar IMFs. At this point, you should readily recognize that all of these have some aspects of polarity within them, but clearly this one has the most nonpolar surface area, so it's going to be the least soluble in water. Determining which one would be most soluble in water would be a bit more difficult, and so we wouldn't ask you to do something like that unless you had an easier way to tell. Pause this video and try this one on your own as well before seeing me work through it. Welcome back. So in this problem, we read that we have a bottle of seltzer water at 25 degrees Celsius that contains carbon dioxide with a partial pressure of 2.36 atmospheres. We're given the Henry's law constant for those conditions, and we want to know what's the mass percent of the carbon dioxide in the water. We assume that the solution is only water and carbon dioxide, and we're given the density of water. Well, what do we know here? We can use Henry's law because we're given the Henry's law constant, we're given the partial pressure. From that, we can find the concentration. So we take the constant times the pressure of carbon dioxide, and that gets us the molarity of carbon dioxide. And this is going to be useful because we want to find the mass percent. We know that the mass percent is the mass fraction times 100%, and we can find the mass fraction by taking the mass of carbon dioxide over the total mass of the solution. Now that we know the concentration of carbon dioxide, we can then use that to find the moles and then the mass. So let's just assume that we have a certain volume here. It doesn't really matter what that volume is, but that helps us to give us some starting numbers. We know that we have the molarity is equal to the same number of moles per 1 liter. And so if we have the 1 liter of solution and we use the density, we can see that we have 1,000 grams of solution. That's going to be used in our denominator here. By using the molar mass of carbon dioxide, we can find the mass of carbon dioxide, which gives us our mass fraction. We can take the mass of carbon dioxide over the total mass to get the mass fraction. Multiply that by 100%, and that gives us our mass percent. Let's try another problem. Pause the video and try this on your own before moving forward. All right, in this question, we want to know how many milligrams of aluminum bromide we would need to prepare a 162 milliliter solution with the bromide ion concentration of 185 micrometers. Let's set up our information here. We can convert the milliliters to liters and the micromolarity to molarity. And this is going to be useful because we need to find, or we can use the definition of molarity given that we have the molarity of the bromide and we have the volume. We can rearrange the equation and solve for moles of solute, and then plug in our values. That means that we would have needed just under 3 times 10 to the 5 moles of bromide ions to have that concentration. Now be very careful, because that's not our final answer. We have to account for the fact that it's a 3 bromide per 1 aluminum bromide and that would get us approximately 1 times 10 to the minus 5 moles of aluminum bromide. Using the molar mass of aluminum bromide, we can then find the mass of aluminum bromide that we would need to meet those criteria. And that's 2.67 milligrams. All right, here's our last question. Estimate the molarity of a saturated solution of potassium nitrate at 50 degrees Celsius. The density of the solution is about 1.4 grams per milliliter. Try this on your own, and then I'll walk you through the process. Welcome back. So, if we're at 50 degrees Celsius, that's right here, which means that we're at 90 grams of potassium nitrate per 100 grams of water. If we're asked to find the molarity, let's start by defining that. We need to find the moles of potassium nitrate and the volume of the solution. Well, the moles will be rather easy because we know how many grams of potassium nitrate we have. To find the volume of the solution, we're going to need to add together the solute and the solvent's mass and use the density. Let's calculate the moles of potassium nitrate. That's going to be the 90 grams of potassium nitrate that we saw was dissolved per 101.1 grams of potassium nitrate per mole. That gets us 0.89 moles of potassium nitrate. Our volume is going to be the mass divided by the density. And keep in mind here, we need to use the mass of the solution because we need to find the volume of the solution. A big error would be to use either the solute mass or the mass of the solvent. So that would get us 136 or 0.136 liters. Then to find the molarity, we can use the moles of potassium nitrate per volume in liters of the solution, and that's 0.89 moles per 0.136 liters, or 6.5 molarity. That's it for this video. Thanks for watching, everyone. If you have questions, you can ask on Piazza, in office hours, or recitation. See you later.